Well, hey, physics folks. Welcome to Doc Onco Physics. Keith Onco here. What we want to look at today is the second of our projectile motion problems, or kinematics in 2 dimensions. In this particular problem, what we have, as we can see on the screen, is we have a projectile launcher sitting on top of a table, an experiment that some or many of you have probably done before. And that projectile is going to be shot from the position up at the top, and it's going to land somewhere on the floor. Okay, and we've said that our initial velocity from the projectile launcher is 9 meters per second, and the angle that it's going to be measured at, and this would be the angle to the horizontal, so this would be theta right in here, is 15 degrees. Okay, the height of the launcher from the ground, we're going to say, is 1.5 meters. So this is going to be 1.5 meters from the ground, all the way up to the level of where the projectile will actually be launched. Okay, so we want to figure out what the range is. The range, remember, is simply x final minus x initial. We're going to take x initial to be 0, as we normally do, using our coordinate system. The coordinate system that we have, let's move that back up there, is going to be like this. And that's our 0, 0 point, x equals 0 and y equals 0. So if xi, initial value for x is 0, then our displacement, all right, is x final minus x initial, and it just simply becomes x final. Okay, so our displacement is equal to x final minus x initial, but if x initial is 0, then our displacement is simply x final. All right, so what do we know? Well, we know the initial velocity is 9 meters per second. However, it's at an angle. In our table over here, all right, we don't deal in angles. All right, we have data for things going on in the horizontal or x direction. We have data for things going on in the vertical or y direction. There's no room for angles. So what do we have to do with that 9 meters per second at 15 degrees? We're going to need to break it up into x and y components. Okay, this is where vector analysis and trig come in more than real handy. All right, you need to know trig, you need to know vector analysis. This velocity vector here, vi, right, can be broken up into an x coordinate and a y coordinate, and that's what we need to do. Well, if this is my angle, and this is 15 degrees in here, okay, I can break this up and say that the cosine of 15 degrees times the hypotenuse, which is 9 meters per second, is going to equal the x component. Right? And when I plug that into my calculator, what I get is 8.7 meters per second. Okay? And so I'm going to plug that right into my initial velocity in the x direction, right? And that's going to be 8.7 meters per second. All right, so I know that. I can also do the same thing for the y side. So the y side is going to be 9 times the sine of 15 degrees. And that turns out to be about 2.33 meters per second. Okay, so I'm going to plug that into here, 2.33 meters per second. Again, very important that we use the table. Right? Helps to keep us organized, and the more organized we are, the easier these problems are to solve. Okay. All right, so I've broken up my initial velocities into x and y components. Now let's see what else I know. Well, I've said that my starting point is at x equals 0 and y equals 0. So my initial value for xi, all right, and initial value for y initial are both 0. What's my final position in the x direction? Well, that's what I'm trying to find. All right, so that's what we would like to know. So I'm going to put a little square around that. All right, this is what we're trying to find right in there. All right. What's my x final position in the y direction? Well, we've said that it's 1.5 meters from the ground up to the launch position. But if this position where we're launching from is 0, 0, right, the ground is in the negative y direction, right? We're coming down here, right? So this point right at the bottom here, where the ball is going to land, the projectile is going to land, it's going to be at negative 1.5 meters because we're going in the downward direction, right? We have our coordinate system. We're going in that direction, negative y direction. Okay, so we know that so far. Do we know v final in the x direction, or the final velocity in the x direction? Well, keep in mind that the velocity in the x direction is initially provided by the launcher. Okay, there are no other forces in the x direction on our projectile, and so there is no acceleration in the x direction on our projectile. And we're neglecting air resistance here. So we know that air resistance will actually cause some deceleration of the ball, but we're going to neglect that for now. Right? And so our final velocity in the x direction is going to be the same as our initial velocity in the x direction, which is going to be 8.7 meters per second. As I just said, the acceleration in the x direction is 0. Now let's look at the y direction. Well, do we know the final velocity in the y direction? We don't, right? So as this ball comes down here, it's got both a velocity in the y direction, it's got a velocity in the x direction. We don't know what the velocity in the y direction is yet because it's going to be gathering speed as the ball goes in the downward position. So we do not know that. We also don't know the time. Time is something that we'd really very much like to know. So let's take a look at what we have and what we'd like to know. So we'd like to know the time. Okay. Well, up here in our equations, right? Here's our equations up in the upper right-hand corner. Which equations have time in them? Well, the first two do. X final equals x initial plus v0t plus a half at squared. That has time. Okay, so we can get time that way. The second equation has time in it, but we don't know v final. Okay, so in order to get time from this equation, we're going to need to know v final. We can get v final, though, using the third equation. V final squared equals v initial squared, we know that, plus 2 times a times the change in position. Well, we know all those things. Okay, I'm going to choose to use the third equation and then the second equation to get time. We could have used the first equation, and in the next problem that I do, we will use that equation to find time. What you're going to find, and what most students don't like, is that in order to use the first equation, we need to use the quadratic formula. We will use that the next time. Okay? But you can avoid the quadratic formula if you choose to take and find the time in a two-step process, which we're about to do now. All right, so let's take the third equation to find the final velocity in the y direction. All right? So v final in the y direction squared equals v initial in the y direction squared. Well, v initial is 2.33 meters per second. So we're going to square that. Plus 2 times a, which is negative 9.8 meters per second squared, times delta x. Well, delta x, all right, is just the same as x final, all right, and that's true in either the x direction or the y direction. So our initial position in the y direction is 0. X final is negative 1.5 meters, so delta x in the y direction is negative 1.5 minus 0. All right, so it's going to be negative 1.5 meters. Okay. All right, so when I do the math here, what I end up with is 5.44 meters squared per second squared plus 29.4 meters squared per second squared. All right, and when I add these two values up, I get 34.83 meters squared per second squared is equal to v final in the y direction squared. Now, before we actually figure this out, okay, we have to keep in mind that what is the direction of our final velocity? It's in the downward position, all right, downward direction, all right, as far as the y coordinate system is concerned. And so when I find v final, it is going to have to be negative. It's going down. All right, remember, we lose the sign because we've got squared terms here. We've got to keep that in mind. All right, so v final is simply going to equal, I'm going to take the square root of both sides now, and v final is going to equal 5.9 meters per second, but I'm going to have to stick a negative sign in there. Okay, so now I have v final. I'm going to plug that into my table over here. Okay, so I've got v final. Now let's see if we can find time. Well, now I can use this second equation because I've got v final, I've got v initial, I've got a, and I can just get t. All right, so let's do that again. So this is going to be the y direction stuff again. So v final, which is negative 5.9 meters per second, equals v initial, which is 2.33 meters per second, plus a times t. Well, a is negative 9.8 meters per second squared times t. Whoops. I'm going to move the 2.33 to the other side, and what I end up with is negative 8.23 meters per second is equal to negative 9.8 meters per second squared times t. And when I divide each side by negative 9.8 meters per second squared, I get a value for t equal to 0.84 seconds. Okay, and I'm going to plug that into my table here, 0.84 seconds. Now remember, time is that one variable that once I know what it is on one side of my box here, all right, I know what it is on the other side as well. 0.84 seconds on both sides. Okay. All right, I've got as much information on the y side as I can possibly get. Now let's look on the x side. What am I looking for? I'm looking for the range. I'm looking for x final. So this is going to be my x calculations now. I'm looking for x final. Well, do I have an equation that will help me get x final? Well, the top one will, right? X final equals x initial plus v0t plus a half at squared. Well, x final equals x initial, all right? X initial in the x direction is 0 plus v0 times t. Well, my initial velocity in the x direction is 8.7 meters per second. Okay, times t, which we just calculated to be 0.84 seconds, right? Plus 1/2 at squared. All right. Well, 1/2 times a. Well, what's a in the x direction? It's just 0 times t squared. Okay, this whole term drops out here because it's 0. All right, and what is x final? My range turns out to be 8.7 meters per second times 0.84 seconds. Let's do that on the calculator here. 8.7 times 0.84 is 7.3 meters. So my range, all right, the distance that my projectile is going to travel from the edge of the table over here all the way out to here is going to be 7.3 meters. Okay, and that's how we find the range. So what are the keys to this? The keys are breaking the information up into x and y coordinates, right? Especially the, oops, let's bring that back up there. The initial velocity. Okay, we've got to break up that initial velocity because the initial velocity was at an angle. All of the data that we plug into our tables has to be either x direction data or y direction data. If it's at an angle, we've got to break it up. Then once you break it up and you have the information in your tables, then you simply use the equations up in the upper right-hand corner to solve the problem. Okay, I hope that helps, and we'll see you next time.